So guys, this is the Excel sheet that has the code, everything. I try to explain in a way you understand. Please pay attention to the formulas. So just choose a cell and put the value of E as given. So all these are given, the E, A, I, and the length. I think this is was deleted or something. So let's say just say L, the length. So number 1, number 2, and the uniformly distributed load is 20. So to get the fixed end moment, the applied force on the node 2 is 50. So on node 1, to equate that, is the applied axial force is negative 50. To equate that, we need 50. So 50 there, and then the shear forces is just WL over 2. So the D2 is what? D2 is the load, the UDL. B5 is the length, so WL over 2, and of course the fixed end moment WL squared over 2. D2 is the weight, and B5 is the length, so squared over 12. So that's a fixed ended moment. And then I note here that assume clockwise moments are positive. So that's important, because if you confuse the directions, then you might get lost. So you do the same assumptions for node 2, so that you get the fixed end moments. So for member 1, the case is a little straightforward. So you put your reactions there, here, and number 1, 2, 3, 4, 1, 5, 1, 6, 1, the same in the horizontal direction, 1, 2, 3, 4, 1, 5, 1, 6, 1, because this part is going to overlap into member 2, so it's important to pay attention. And basically just put, this is EA over L, and is up to the fourth is negative E over L, and is symmetrical. So if you check here, symmetrical, and you know this is 0, this is 12 EI over L cubed, this is 6 EI over L squared, 0, negatives, negative of this one, and this are the same, and so 0, 6 EI over L squared, 4 EI over L, 0, this is negative of that, and this is half of that. So once you get the first 3 here, to get the second half is very easy, because there is a relationship. For example, the fourth one is usually the negative of the first, so you can see, very easy. So this this, okay, the column M and column P have a relationship such that column P is the negative of M, the same. So Q is negative of this it is symmetrical above the diagonal, and this is the case. So for the first one, I think is very easy. And then the fixed ended moments, you put them appropriately, so as you can see, and of course the displacement and the deformation matrix. So the deformation matrix, transformation matrix. So just to show, we put we assumed clockwise is clockwise and also refers to angles. So clockwise is negative, so it was negative 56.31. If you convert into radians by dividing by the by 57.29, this is what you get, negative 76. The negative indicates the direction divided by radians. That's the value you get. So just input the formula for the transformation matrix. So cos the angle, sine the angle, negative cos the angle, sine. So incidentally, the only values are these. The rest are 0, and of course, this mid value is 1, and the same. So this is cos sine negatives, no, cos negative sine. So this is cos negative sine. This is also cos negative sine. But note that this the angle here and the angle here are different. Sometimes the angle is the same. If the angle is the same, it's even easier. So it's easier to solve. Once you sort out this, all this is 0. So that's all you need. And you also need the transformation, the matrix, the local member matrix in the horizontal direction before orientation. So just assume the member is in the horizontal direction. So this is the matrix. So this is just direct substitution as in the previous case. So I think a little straightforward. So once you solve the member matrix, so this is the one that is slanted. So you already have the K, the stiffness matrix when it is not oriented, and then the transformation matrix. So to solve this is already calculated. So maybe I delete so that you can see. So for example, first to multiply the matrices, you need to select yes, so this is where we want the multiplication, but this is already known. So let me try to clear everything. Clear. So you see, so this is the part we need. This equals, please pay attention now. Sorry, you must highlight the if the resultant matrix is 6 by 6, the resultant of the multiplication is 6 by 6, please highlight 6 by 6 area. So 1 2 3 4 5 6, okay, and then write equals, then use what you call m multiply, m mult equals m mult, then transpose. So transpose of then you highlight the matrix whose transpose you require, and then comma the second matrix you want to apply, which is the K. So highlight that, you highlight that. Once you do that, close your bracket, and please pay attention, Control Shift then enter at the same time, then you get your answer. And so this is TT times K, and then we need to apply this, multiply this with the same transformation, with the transformation matrix now. So a little tedious. There is a shorter way I'll show you later, but just so you know. So this is, can clear this. So after you highlight, you say equals equal to m mult. So multiply this. Once you then you select the then you select the transformation matrix, Control Shift and enter. Alright, so you get your solution. That's one way. Another way, a simpler way actually is, I don't know whether which one is simpler, depends on you, but I think this is simpler. Equals, instead of doing so many things, we can actually multiply three matrices together, but use some trick because m mult can only multiply two arrays. So please pay attention. So m mult, m mult, m mult. So first you have to multiply the m mult of the transpose m mult of the transpose of this. So you multiply the transpose and the transpose with now the K matrix. So you finish multiplying that. So the transpose multiplies is the correct array, and then now you include the array number 2, which is T. If done correctly, the solution should be the same. So place after that, Control Shift and then enter. The solution should be the same. Alright. So we have had this has now been transformed to the correct orientation. Incidentally, so very interesting. So it's still symmetrical. So maybe I was wrong previously. Looks like even after transformation, then it is still symmetrical. Yes, so I think so it's fine. So symmetry is a key issue. I think in this case there are some angles perhaps the symmetry may no longer hold, and the fixed end moments are 0 in this case because the second member is not loaded. There is no load in the second member, so the fixed ended moments are 0. So what is remaining now is to assemble the global stiffness matrix, which consists of just the two matrices you already assembled. So global stiffness matrix, I think simple, because if you arrange 1 2 3 4 5 6, so you only know this, you only worry that this area is are going to overlap. The rest you just copy. For example, from 1 3 to 6 actually is just the same as so you can see, just to help you see the point, escape page. So let me clear so you can see how to copy. So that equals that and Control Shift and enter, and that's already copied. Right, and then the same can do this part, is just this part here, is just from member 2, so this part. So just demonstrate a bit how to make the stiffness, the global stiffness matrix equals this. Control Shift and Enter together. Alright, and then to demonstrate to you the overlapping part, we clear this overlapping part equals the equals this part, that part, that part plus this part. Control Shift and Enter, then you should be fine. And then you literally copy the rest. So this part is missing. It means if it's not there is 0, and this part is 0, and of course this part you copy from the second. So just to highlight, so this is member 2, this is member 2 matrix. I don't know which color to use, so maybe which color, this member 2, and this is member 1. So very simple. So you can arrange all the reactions you want. So this is the reactions, this is the K matrix, and this is the deformation or displacement matrix, and this is the fixed ended moment. So here, to help you solve, you need to know, apply the boundary conditions to help you in the solution. So the boundary condition node 2, -50 is indicated. The shear force is 0 because there is no support. If there is no support, the shear force is 0. So support is like A, there's a support, and C, there's a support. So let this A is 1, B is 2, and C is 3. So that said, so external loads at node 2 are sorted out. At node 3, because of the roller, then N3 is 0, that is known. And also the moment, also the moment, because of the roller is a pin, the moment is 0. So you isolate these points as written. So this corresponds to 4, 4. You can isolate them here, 4, 5, 6, 7, 8, because these degrees of freedom correspond to the ones whose external loads are known, correspond to 4, 5, 6, 7, and 9. Remember, we have skipped 8 because we don't know this. So 4, 5, 6, 7, and 9, those are known. So that's why we isolate 4, 5, 6, 7, and 9. So 4, 4, 5, 6. So for example, 4, 4, you pick this one, 4, and column 4. So you pick this one. So you pick 4, 5, 6, 7, and 4, 5, 6, 7, and 9. So you can basically copy this. You can literally copy escape. Sorry, you can literally copy this part 4, 5, 6, 7, and 9, and then copy the, okay, whichever way you copy, I think that's up to you, but the most important thing is you understand the concept. and then once you isolate, so of course with the fixed and corresponding fixed end elements, with the corresponding fixed end elements, as you can see here, so I will color them because already with this closest, okay, I'll show you. So this is the external reaction, and this is the P matrix. Sorry, this is the fixed end moments, and these are the external loads. So then you can say that equals, okay, I need to clear so you can see. So the P matrix, sorry, escape. So escape. The P matrix equals these values minus, because when these ones cross the positive sign become negative, so Control Shift Enter, yeah, and then you have your solution. So I think there should be equal sign somewhere, and maybe I sacrifice this. Okay, please note this is 5, just to avoid confusion. You sacrifice equal sign there. Okay, equal sign, and also put 5 there. No, it will not agree. So there's some equation, there's some equal sign here. I don't know how to, maybe try with this. Yeah, just to know there's an equal sign. Oh no, this doesn't look good. Okay, maybe sacrifice. So please note the second one is a 5. I'll put equal sign to avoid confusion. So escape. So then once we deal with that, we don't need them. Let's color this now. Some color, maybe red, to block them out, because we already dealt with them. I could type it fresh, but I think to avoid typing so many things. So I've dealt with this, so I only have these two matrices. What do we do? So this is K. I need to multiply by the inverse of this. Once I multiply this by the inverse of this, I get the identity matrix you can see here. And let's say if I multiply the P matrix with the inverse, I get the solutions. So just to demonstrate to you, so here can clear, also pay attention, equals M inverse, yeah, M inverse, I think M inverse, no, it's not, M inverse of M inverse, sorry, you have to start with M mult, because you multiply the inverse, M mult, so the first ray is the inverse, the first array is the inverse, this is not right, M inverse, comma, by itself, so the same array, Control Shift Enter, identity matrix, good, and then let me clear this to see, so you can see the solution by yourself, equals M inverse, M mult of M inverse of this, M inverse of that times the P matrix already determined. Control Shift Enter, then you have your solution. You can compare, you can see in the same range. So then once you solve the indeterminacies, you can take back into the global matrix equation as shown down here. So these are the reactions. Yeah, these are the these are the reactions. This is the global stiffness matrix. You can add your displacements and the fixed-ended matrix, the fixed-ended moments. Then you're able to solve everything. For example, here, just to demonstrate just one how to get. So for example, the n1 equals what? Equals this matrix. No, escape. Yeah, equals a mult of the first row and the column, then plus this. And please don't forget Control Shift and Enter. So all this you can, and you get your reactions. So you can see how easy. So even if the matrix is 16 by 6, 16, 12 by 12, 8 by 8, you are able to solve. Thank you very much. I hope you can now use this to record your own. Goodbye. Hope you enjoyed this.